looking some more at the relationship of the binomial coefficients. It all begins with our binomial theorem that we saw yesterday. So every one of these problems, we pretty much just start with the binomial theorem, which, as a reminder, in some notation, it looks like that. So the general term, nck x to the power of k, we're going from k equals 0 to n. If we were to expand the thing out, there it is, nc0 plus nc1x, and so on, and so on, and so on. So we might get a question like this. Find the values of, so the sum of nck going from 1 to n. So in other words, nc1 plus nc2, and so on. Well, it starts with the binomial theorem, so that's the first thing I write down. And then I just compare and say, well, where am I heading to? What have I got? How can I make them the same? Now I notice where I'm heading to, there is no x there. So how can I get rid of that x? Well, if I let it equal 1, because 1 to the power of anything will always be 1. So let x equals 1, put it in the left-hand side as well, of course, and I get 2 to the power of n is equal to the sum from k equals 0 to n of nck. Not quite what we want. We want 1 to n, not 0 to n. But before I move on to that, that in itself is interesting. If you think about it, what it's basically saying is any row in Pascal's triangle will add up to be 2 to the power of n. So whichever row it is, because that would be all the coefficients added together. We don't want the one where k equals 0, so I just simply take it out. So that k equals 0 gives us nc0, but then I would also have the sum from 1 to n that I want. Well, nc0 we know by definition is always equal to 1. So move that to the other side, and we have our answer. So k equals 1 to n of nck will be 2 to the power of n minus 1. It's all the odd ones. So nc1 plus nc3 plus nc5, and so on. So I just want the odd ones. But again, it always starts with the binomial theorem. I want the odd ones. Well, I'm going to start this one the same as I did the last one. If I make it equal to 1, and you'll notice this time I'm writing all the terms down, because that's what the question's got, so I'm sort of trying to get to that. I've got all of the terms will be 2 to the power of n, but I don't want all of the terms. So now what I'm going to do is I'm going to substitute in -1. You see, if I substitute in -1, then -1 to the power of k will create an alternating pattern of plus minus, plus minus, plus minus. So I've got nc0 minus nc1 plus nc2 minus nc3, and so on. And on the left-hand side there, 1 minus 1, well, that's going to equal 0. Basically, I've got simultaneous equations now. So if I just want the odd ones, what have we got to do? Add or subtract? Add would get me all the even ones. Subtract will get me all the odd ones. So looking at equation 1 and equation 2 there. So if I subtract, I end up with, well, 2 times all the odd ones. So divide both sides by 2, and I've got that the odd ones will always add up to be 2 to the power of n minus 1. Interestingly, that now means that all the even ones must add up to be what? What must the even ones add up to be? 2 to the power of n minus 1. So it'll be the same. The odd ones and the even ones add up to be the same, because, think about it, you'll have 2 to the power of n minus 1 plus 2 to the power of n minus 1, which is 2 lots of 2 to the n minus 1, which is 2 to the n, which we've already seen, that is what they all add up to. Oh, k times nck. Always start with the binomial theorem. There it is. How can I get something that looks like that? So I'm trying to get k in front of the term. What mathematical operation do we have that would get that power and bring it to the front? Well, that's differentiation. So if I differentiate both sides of the binomial theorem, so on the left-hand side, anarchy, bring down the power, lower the power, diff the inside, which in this case is just 1. On the right-hand side, well, the k now comes to the front, the power changes to k minus 1. All right, now let's compare again. So the only difference now, well, actually there's a couple of differences I should say, but if I'm just looking at the general term, so just looking at the general term, the only difference now is that x. So I'll do that trick again. Let's make x equal 1. We get, well, from 0 to n, So once again, I'll extract k equals 0. So in this case, it happens to be 0 anyway. But then we got k equals 1 to n of k, nck. On the left-hand side, we've got n times 2 to the power of n minus 1. And so we have our answer. This is a beautiful one. By equating the coefficients of x to the power of n, so they've given us a clue on how to approach this. On both sides of this identity, which must be true, because when you multiply, you add the powers, so they would be the same. We're going to show this wonderful expression here. We've used the different notation for nck there, but all they're saying is nck squared. So all the binomial coefficients squared, if we were to add them together, we'll end up with 2n factorial over n factorial squared. Starts with the binomial theorem. There it is. I'll write it out because I want those coefficients squared. Let's have a look at the coefficient of x to the power of n. That's what they've told me to do, so we may as well do what they've asked us to do. Of x to the power of n in 1 plus x to the power of n, which is what I've written down, but we're going to multiply that by 1 plus x to the power of n, the same thing. In other words, I'm multiplying these two things together. But I'm only interested in the coefficient of x to the power of n. So if I was to start with nc0, well, nc0 I would have to multiply with the very last term in the other one, so ncn, and that would end up with x to the power of n. If I go to the second term, nc1, that would have to be multiplied by the term with x to the power of n minus 1, because that would create x to the power of n. And we could keep matching all these pairs. So the nc2x squared would have to be multiplied with the ncn minus 2 x to the n minus 2. And we would keep going, and eventually we'd come to the last one, and so the ncn x to the n would be multiplied by the nc0 in the first one. But every one of those has x to the power of n. So whatever they all add up to, that's going to be our coefficient. Well, let's tidy it up a bit. So there it is. There's the coefficient. I'm not actually interested in x to the power of n, just the coefficient. But I can make that neater if we remember one of our Pascal's triangle relationships. Remember, it's symmetric. So nck and ncn minus k will always be the same thing. So nc0 times ncn is in fact nc0 squared, because ncn is the same as nc0. nc1 times ncn minus 1 is in fact nc1 squared, because they would be the same thing. And so on and so on and so on. We get to the last one, and that nc0 would be the same as ncn, so we've got ncn squared. So we do actually have all of the binomial coefficients squared. And I'll just write it in some notation to match what they've been asking me to prove. So, all right, I know that part of it. Now let's look at the coefficient of x to the n on the other side. 1 plus x to the 2n, which is just a straight binomial expansion. And if we were to expand the whole thing out, we'd get something like that. The power now is 2n though, not n. So I'd have 2nc0, 2nc1x, and so on. Somewhere in the middle, there would be the term with x to the power of n. And its coefficient would be 2ncn. But it's the only term that would have x to the power of n. So in that part, I know all I'm looking for is that one. So the coefficient of x to the power of n for that one is 2ncn. But remember, we said these two things were the same. Their coefficients, therefore, can't be different. So because we know that is true, then this must be true. Because equating the coefficients, they've got to be the same thing. Not quite what they asked me to prove, though. Left-hand side's okay. I've got to play around with the right-hand side. Let's put it in the factorial notation. That would be 2n factorial. And when you're writing 2n factorial, by the way, make sure you put the 2n in parentheses, because otherwise it looks like you're saying 2 times n factorial. So it's 2n factorial over n factorial n factorial. Well, n factorial times n factorial is n factorial squared, and that is the relationship they asked us to prove. So a little bit involved, that one. And can I tell you, when this syllabus first came out, they thought these sort of questions were not in it. That's what a lot of teachers thought. in 2020, the very first of the new course, this question came up. Use the identity 1 plus x to the power of 2n to equal 1 plus x to the power of n on 1 plus x to the power to show that this expression, which essentially is what we just did in that last example. And that was the first part of the question. And there was uproar. People go, hang on, this isn't in the syllabus. And they've gone, oh, yes, it is. But you'll notice it's part A. And it went on and turned it into a really good question. Because it then turned it into a combinatorics question. And said, all right, you've got a club, and your club has 2n members, n women and n men. A group consisting of an even number of members. So, interestingly, they're saying 0 is a group. I wouldn't call that a group. If there's no, how can you have a group with none in it? But anyway, they in their questions defined that to be a group of 0. But then you could have a group of 2, a group of 4, up to a group of 2n. Reason it's even because they're saying it always has an equal number of men and women in the group. Show giving reasons that the number of ways of doing this is 2NCN. Well, I know that the number of ways of choosing k men from a group of n men, because that's what we've got n men to choose from, would be NCK. I know that to be true. And I also know the same would happen if I'm choosing k women from n women. That would also be NCK. So if both things have to happen, well then we would multiply that together, which is NCK squared. Not what they've asked me to show. However, we could rewrite it the total of different ways. So remember, we're saying there could be 0 in the group. Don't know how, but there could be 0 in the group. That would be NC0 squared. Another possibility is that there is 2 in the group. Well, that would be NC1 squared, because 1 male, 1 female. There could be NC3, could be NC4, 5, and so on, for all the different possibilities of having the same number in both groups. In other words, we would add up all of these. Well, that looks familiar. That, of course, is what we did in part A and showed that that was 2NCN. So, in fact, there it is. There's the answer they want. The number of ways of doing this is 2NCN. But it didn't stop there. So now, from the group that you chose in part B, one of the men and one of the women are selected as leaders. Show giving reasons that the number of ways to choose the even number of people, then the leaders, is this. Well, how many ways could we choose the leaders then? We know that there's NCK squared ways of choosing the group. So you've got to choose the group first before we can choose the leaders. That's what this is saying. Choose the group, then select the leaders. So now we're going to choose the leaders. Well, one's got to be a man. Well, how many choices do I have? Well, K. There's K men. And now I'm going to choose the women. Well, how many women were there? There were K. So I'll multiply by K squared in other words. But every group we would do that with. So it will be the sum from 1, because I still don't believe 0 is a group. But in this case, there's no way I could have 0 as a group. Because how can I choose someone to be the leader if I haven't got anybody? So this time the sum has to start at 1. When you're doing a solution for something like this, you would need to explain why all of a sudden does your sum start at 1 rather than 0. So you need to explain that. Well, this is why. And so that's the answer they were looking for. 1 squared, NC1 squared, plus 2 squared, NC2 squared, and so on, and so on, and so on. Okay, but it did not stop there. The process is now reversed, so that they're going to choose the leaders first. 1 man and 1 woman are chosen first. Then the rest of the group is selected. Still an even number of men and women. By considering this reverse process and using part B, find an expression, well, simple they say, find a simple expression for the sum in part C. So we're choosing the leaders first. We haven't got the group. So that now means I've got n possibilities, not k, because I could choose from any of the men. And same for the women. I could have any of the women. But now I've got to get the rest of the group. But to form the rest of the group, I no longer have to choose k, because I've already got the leader. I now have to choose k minus 1. And I'm no longer choosing from n because I've grabbed one out to be the leader. Now I'm choosing from n minus 1 men. In other words, n minus 1c k minus 1. And then we do the same for the women. So in other words, the total ways would be n squared, choose the leaders, times n minus 1c k minus 1 squared, choose the groups, but then the sum would go from 1 to n for all the different possibilities. I could have a group of 2, a group of 4, or a group of 6, and so on, so on. That's what I'm looking at if I was to expand it out. N squared, n minus 1c naught squared, plus n squared, n minus 1c 1 squared, and so on, and so on. Well, let's factorise out the n squared and have a look at what we've got. It's the sum of the binomial coefficients squared. Well, we've already worked out a simple result for that. Sure, it was nck we were using. It doesn't matter. I could have n minus 1. It's still the same result. Our result when we were doing nck ended up being, it was 2ncn, wasn't it? We end up with 2ncn. Well, the only difference here is instead of n, I've got n minus 1. So it'll be 2 outside of n minus 1, cn minus 1, tidying that up. There is the simpler expression that they're looking for. N squared times 2n minus 2 cn minus 1. So 15D is just basically playing with the binomial theorem and coming up with different relationships and what have you.